will be talking about his company, Schlotter, the leading solution provider for surface technology. Phil, over to you.
Thank you, Oleski. I'll just share my screen. Hopefully we can, right, hopefully you can see that. First of all, thank you very much to the DSM network team for asking me to talk today. And thank you to James from Poton and Shay from Queen's University Belfast. I'm in very esteemed company today. So I hope you're all well. I seem to have the Friday.
Sorry to interrupt you, Phil.
Yeah.
We can't see your screen.
You cannot see my screen.
No.
Beg your pardon. Okay, you should be able to see my screen now.
It's better now, yes.
I beg your pardon. Okay, I won't start my dialogue again because I'm sure everybody heard that. Okay, can you see that presentation screen now still?
It's working.
In the presenter's mode.
Okay, thank you very much. Okay, so well, I hope everybody is well. I seem to have the Friday afternoon slot after lunch, so I'll try and keep things lively, moving along. For those of you actually watching a video, now's the time to stop fast forwarding. I'm sales manager for Schlotter UK. My background is as a supplier to the surface finishing and metal finishing industry. I graduated in too long ago to mention, 1985 actually, in the days of polytechnics, which many of us still remember. At Schlotter, we are suppliers to the metal finishing industry, the GMF, as we know it, the general metal finishing industry. In the UK, we're also a major supplier of industrial paint. Actually, if you look in your local supermarket, you'll see many bottles on the shelves coated with our product. But let's get back to electroplating. First of all, I'd like to introduce Schlotter as a company. So I'll quickly whiz through this short presentation, you'll be pleased to know. And after that, I have 3 short presentations on basics of electroplating, surface preparation for electroplating, and periodic reverse pulse plating in electronics. I can answer any questions as we go along. I think it's traditional to wait for pauses, but happy to discuss anything with anybody at any time, basically. Okay, introducing Schlotter. Who is Schlotter? Schlotter started in 1912 in Germany. We're still a family-owned company in a 4th generation. We're not owned by a venture capitalist group. We're suppliers to the electroplating industry. So we supply electroplating solutions, additives, equipment such as plating lines, and we support our customers with technical advice, analytical services for their solutions and their plated deposits. We employ 300 people or there and thereabouts worldwide. Okay. Locations, we've got 6 locations worldwide: Singapore, Ireland, China, Germany, Sweden, and us in Pershore in Great Britain. Here is Max, who started it all off in 1912. In actual fact, many of our customers, I think, are under the impression that Schlotter are a big group or a big organization full of little labs, full of people with long little beards and glasses. And this proves the case that that is actually the case. Yeah, that was Max. That's who started it all for us. I'm not going to dwell because I'd rather get on to talking about interesting and practical things, if that's okay. Historical milestones for the Schlotter company, lots of milestones with benchmarks and awards. We're probably best known historically for our tin plating technology. We are very research orientated. 2 main areas: PCB and electronics, printed circuit board and electronics. GMF, general metal finishing, otherwise known as corrosion protection. Lots of employees and developments chemists working in those areas. More pretty pictures of our analysis equipment. That's just to demonstrate. I won't hang around on these pages. It just gives you a background of who we are and where we're coming from and what our capabilities are. Obviously, we have a technical center. Those there are development plating solutions, plating cells. That's where we take the technology out of the lab and apply it to the real world effectively. So those, and that's where we find out how we actually make our solutions work. We cooperate with a lot of people. Customers are our partners, not just customers, a lot of different institutions that we work with. In a discussion with Shay earlier on, we were advocating, and I still do advocate very strongly, collaboration between industry and academia. I think we can do a lot to improve that as we go forward. One of my favorite collaborations at the moment is actually with Siemens. We're working on hydrogen fuel cells for hydrogen and electricity generation. We're looking at increasing the efficiency of fuel cells. As you can imagine, the pressure's on at the moment. Again, these are some of the R&D roadmaps. These are the projects that we're working on. Materials and hydrogen, as I mentioned, 5G, 6G technology in printed circuit board manufacture, plastics metallization, connectors. Our roadmap for R&D, digital chemistry, i.e. smart services, decarbonisation of surface technology, and closing material cycles. Basically environmental responsibility, as I would read that. So thank you for your attention on that. I think that gives you a little bit of an overview of where we're coming from Schlosser's point of view. What I'd like to do now is to run a short presentation on the basics of electroplating. It allows me to shut up, although my voice carries on because there is a soundtrack to this. So let's just play it.
Hello, I'm Phil Norton, and this is a short presentation which introduces the basic elements of electroplating. Electroplating is essentially a reaction driven by electricity in the same way that we use electricity to power other processes such as a motor, a light bulb or an electric oven. In this equivalent, we are using electricity to coat objects with metal. So, what items will we need to coat with metal? Well, the list seems endless, and electroplating applications include coating functional items where a metal coating protects the item and makes it look good, for example plating with nickel, chrome or zinc alloys. To protect the item from corrosion, commonly using zinc or zinc alloys. To modify the physical properties of the object, for example using tin or bismuth. Coating decorative items, for example ornaments or jewellery with gold or other precious metals, or to provide solderable and reliable electrical connectors using gold, tin or silver alloys, and to provide electrical circuits and many other electrical components using copper plating. So how does electroplating work? The easiest way we can work on the complete surface of an object, represented here by a disc shape, is to immerse that object in a liquid. We call this liquid the electrolyte. The electrolyte contains the metal which we want to coat or plate onto the surface of the object. We can achieve this because while most metals are insoluble, they can exist in other forms, many of which are soluble. We just have to pick the right chemical compound to use, in this case a metal salt. For example, copper metal is not soluble, but copper sulfate is. We can dissolve copper sulfate in water and use this as the basis for our electrolyte. So let's use copper plating as our example. Here's our disc, in a copper electrolyte. Now here's where the electricity bit comes in. Let's make a circuit by putting in a metal electrode, connecting the object to be plated to a power supply, and connecting the electrode to the other end of the power supply. This could be a battery or anything which gives a continuous current of electricity. Let's switch it on. The electric current moves around the circuit, which includes the copper electrolyte. An interesting thing happens in the electrolyte. The copper moves the opposite way to the electric current and sticks itself to the object, building up an increasingly thick layer for as long as the electric current is moving. This is the basis of electroplating metal deposits. The same principle applies to all electroplating regardless of the metal being plated. As you can imagine, life is never that simple and many variables apply, but the fundamentals remain constant. Michael Faraday, considered by many to be the discoverer of the electroplating principles we use, was right about many things. Here's a few basic rules to remember. The electrodes we use to complete the plating circuit are called anodes. These can be made of the same metal being plated, in which case they dissolve during the plating reaction. They can be inert or insoluble, for example steel anodes in zinc plating or platinized titanium anodes used for gold plating. The anodes and object being plated must be connected the right way round. Positive to anode, negative to the object being plated. Otherwise horrible things will happen. It's important to use DC, not AC current when electroplating. AC, or alternating current, is what's supplied to all houses and factories and must be converted to DC, direct current, for electroplating using a rectifier. The electrolyte itself contains other components as well as the metal to be plated, and all these are there as part of the electrolyte formula, and can include acids, for example sulfuric acid in copper plating, or alkalis such as sodium hydroxide in zinc plating, both of which help to keep the metal in solution. Dissolved solids like salt, which increase the conductivity of the solution. Proprietary additives which modify the plating reaction, for example levelers, which make the deposited metal smooth, brighteners, which make the deposited metal bright, grain refiners, which modify the structure of the metal being deposited, and antioxidants, which help stabilize the mixture. All these can result in a complicated mixture, and it's important to maintain the electrolyte properly so as to obtain consistently good plating results. This is where specialist suppliers can help. What sort of items can be electroplated? Well, anything metallic or electrically conductive can be plated, as long as it is cleaned and prepared in the right way. This is the subject of a separate presentation. If an object is non-conductive, for example a football boot, the surface is normally coated with an electrically conductive material like graphite or carbon before plating. Electroplating is a fascinating world with many different facets, influences and applications, but the basic principles are simple, as I hope we've outlined here. Thank you for your time and attention, and I hope this has been a useful presentation for you.
Okay, thank you very much for listening to that. That was probably very basic for a lot of the audience, but I hope parts of it were constructive and instructive. I often challenge people to look at their own assumptions. I spotted something in that presentation which is a little bit of a topic for me at the moment. I actually state in that presentation that electric current runs through an electrolyte, and I'm actually going to challenge that. Maybe somebody would like to talk to me about it after these presentations. Electric current, I believe by definition, is movement of electrons, and I question whether electrons actually move through a plating solution. It's all about surface dynamics and what happens on the cathode and the anode. So I'm going to move on from that and let's talk about cleaning and surface preparation. One of the first things that I learned in industry, I don't know whether it's still around, but we talked about the 7 Ps, which isn't taken from Mr. Popper's Penguins film, but it actually stands for proper planning and preparation prevents a pitifully poor performance, which applies to many things in life, but very specifically that applies to the metal finishing industry. So let's talk about cleaning.
Hello, my name is Phil Norton, and this is a short presentation which outlines the fundamental principles and some of the science involved in surface cleaning. Regardless of the finishing process being carried out, the cleanliness of the surface being treated is the very first consideration. Without a clean substrate, the complete finishing operation itself is at an enormous risk of failure. So, it is important to understand the fundamentals of cleaning and pre-treatment of surfaces so as to be able to achieve consistent success. We are all familiar with cleaning operations such as these. But what about when we need to clean something as big as this? Or a few million of these? Or inside a 200 micron diameter hole in a circuit board, seen here highly magnified? Or perhaps a fragile piece of decorative art? For this, we need specialized chemical processes. Cleaning a metal substrate prior to metal finishing is the most significant area we will focus on in this presentation. Specialist formulations of liquid cleaners enable this process to be carried out by immersion only, without any mechanical intervention. So, what are we dealing with? What exactly is a clean surface? Typically, we are looking to remove surface contaminants such as oil and grease, often used in machining as a lubricant and for cooling. Dirt, picked up during handling and storage perhaps. Debris, often from machining operations, which can be embedded into the surface. Metal oxides, the most obvious example of which is rust on steel. We want to see a nice clean metal surface so we can subsequently electroplate, paint, passivate or carry out any surface engineering process without subsequent failure. For industrial scale cleaning, tanks of suitable size are used, typically between 100 litres capacity or up to 10,000 litre capacity, for example, with lifting systems if necessary. Important aspects for effective cleaning include temperature. This can be anywhere from ambient to 90 degrees centigrade depending on what needs to be cleaned. Generally, higher temperatures increase the effectiveness of the cleaning operation, and general purpose cleaners commonly operate at 60 to 70 degrees centigrade. However, light fingerprint removal can be achieved at lower temperatures, for example 25 to 30 degrees centigrade. Agitation. Some agitation is an advantage to move the cleaner solution across the surfaces to be cleaned. Filtration. Weir systems are often incorporated into a tank design so as to remove oil and grease which can float on the surface of the cleaner. There are different types of immersion cleaning. The simplest is soak cleaning, where parts are simply immersed in the cleaner with no additional action. This is often quite sufficient if the cleaner is formulated correctly. Additional techniques can be used to enhance the effectiveness of the cleaning operation. Electrocleaning is widely utilised for metal surfaces and involves passing a current through the surface to be cleaned. This generates a lot of gas on the surface, which has a type of scrubbing effect. The polarity and strength of the current can vary dependent on the metal being cleaned. Ultrasonic cleaning uses a high-frequency pressure or high-frequency sound which induces cavitation bubbles on the surface, which in turn dislodge contaminants. You can normally hear a very high-pitched screaming sound during this process. Pickling is a common type of cleaning which simply utilises strong acids such as hydrochloric acid to remove oxides from metal surfaces, normally mild steel. Sometimes additives are used in pickles to prevent the metal being attacked, in which case an electric cleaning stage must be used to remove the additive from the surface afterwards. A combination of cleaners is often utilised in sequence. For example, for mild steel, a strong caustic cleaner followed by a rinse, and a pickle followed by a rinse, and finally an electroclean and rinse. For non-ferrous, a mild alkaline cleaner or an acid cleaner to prevent surface attack, a rinse, and an electric cleaner followed by a final rinse. So, what's in these cleaners that make them so effective? Immersion cleaners are a combination of chemical elements, typically, but not all, of the following. Builders. These build cleaning capacity, the basic building blocks to support the functionality of the cleaner. Tensides for emulsification. In other words, these ingredients encapsulate oil and grease so that can be removed from the surface. Alkalinity. Strong alkalis chemically react with oils to make them soluble in water. Acids for the removal of metal oxides. Surfactants, which reduce surface tension so that the other ingredients in the cleaner can get to the surface and do the job. Solvents, sometimes used to remove oils and grease. Complexants, these hold contaminants in the solution so that they don't interfere with the cleaning process. And inhibitors, these are used to prevent strong chemicals and acids from attacking the substrate. The builders commonly include silicates, phosphates, borates and carbonates, and these build a matrix to support the other components, increasing the effectiveness of the cleaner. They can work together to hold dirt and contaminants in the solution. Tensides are synthetic organic compounds with interesting chemical characteristics. They can coat oils and grease and make them effectively soluble. In this idealized model, the substrate which needs cleaning may have oils on the surface. The tenside molecules attach to the oil and then form a layer around the oil to hold it in solution. Tensides can do this because, as these diagrams show on a microscopic scale, the tenside molecules are made up of two parts. One end loves water and the other end loves oil and hates water. So the bit that hates water will attach itself to oil. If enough tenside molecules do this, a particle or drop of oil can be successfully held in water. There are many types of tensides, all with different properties. So using the right type is all part of formulating the right products for the right application. Alkalis, commonly potassium or sodium hydroxide, react with oils and grease to change them into soluble components. This reaction is often called saponification. It's why your fingers feel soapy if you get oven cleaner on them. Acids are used to remove oxides from metal surfaces. Choosing the right acid and concentration is essential. For example, nitric acid will quickly dissolve a copper surface and hydrochloric acid will dissolve a zinc substrate. A common example is hydrochloric acid to remove rust from steel. Surfactants reduce the surface tension of the liquid so that the cleaner can wet the surface better and enable other active ingredients to work properly. That's why we use surfactants in domestic cleaners, not just hot water. Solvents are used as a very effective means of removing oil and grease from a surface. For smaller parts, vapor degreasing can be used, for example propyl bromide, where the part to be cleaned is held over the hot solvent so that only the solvent vapor comes into contact with the part. The dissolved grease drips into the sump and off the part. Solvents such as methylpyrrolidine can be used to soften and remove epoxy during printed circuit board manufacture. Complexants can be used to hold dissolved metals and other elements strongly in the cleaner to prevent them further contaminating other surfaces. Strong complexants, however, are difficult to deal with when the cleaner has to be disposed of. All of these elements are combined in many different ways to provide cleaning solutions which are extremely effective in providing perfect substrates for further surface treatments. I hope this has been a useful presentation and overview, so thank you for your time and your attention.
I hope that gives an overview of just how complicated a cleaning procedure can be and what's involved in developing cleaning applications and the formulations that are involved. I think that really does highlight as well the close relationship between suppliers and consumers in the surface finishing industry. I'm going to move on now to the final short presentation, which is about pulse plating, or periodic reverse pulse plating, as we call it in printed circuit board manufacture. I'm sure many people are familiar with circuit boards. It's something that we're heavily involved with at Schlotter, and generally in manufacturing on the electroplating technology. So your circuit board is basically a device for enabling thousands of individual connections to be made. Without your circuit board, your average electronic device is going to be the size of the room with all the wires connecting your actual components. So they're complex things. To actually make connections, we achieve this in the circuit board by drilling holes in our circuit board. To make the connection, we have to make those holes conductive, and then we have to plate copper down them. Some of these holes are, for example, 0.1 millimeter wide in diameter in substrates up to 3.2 32 millimeters, so 32:1 aspect ratio. Getting electrolyte in and out of those holes and actually getting 25 microns plated consistently down the hole is a challenge, but we can do it. So I'm going to run the final short presentation on pulse plating.
Hi, my name is Phil Norton, and this is a short presentation which gives an overview of pulse plating at Schlotter. Pulse plating is used in the printed circuit board manufacturing industry as an effective means of maintaining product reliability and manufacturing efficiency as the complexity of circuit design continues to increase. Technology such as 5G places high demands on circuit complexity, commonly requiring plating in 5mm boards with 30:1 aspect ratio holes. Aspect ratios of 10 or 20:1 are commonplace. But we still require consistent copper thickness, good plating speed, consistent physical properties of the plated deposit, and, importantly, a process which is easy to control and maintain. At Schlotter, we know about pulse plating. We were first to develop a functional additive system and installed the first process in 1989 in the UK. We have continued to develop and refine our processes to keep pace with evolving technology. The Schlotter Coupe CU110 pulse plate process is a well-established system with a wide customer base. The copper deposit is ductile, fine-grained, and the process is maintained with a single additive on an ampere-hour basis. For routine chemical maintenance, well, there's none required. There's no regular carbon, permanganates or peroxide treatments. There's no requirement to analyse for total organic content. We have closely monitored the performance of CU110 baths. The deposit qualities remain consistent despite build-up of byproducts and organics. Process control is straightforward and requires a chemical analysis of copper, acid and chloride, and a wholesale check to establish the brightener concentration. Additional CVS analysis and deposit ductility testing can be provided as part of our Schlotter customer support. CVS is not required on site and is normally carried out monthly to ensure the process trend is under control. Process parameters. The process is easy to maintain within wide parameters for temperature, pulse forward and reverse current density, and time cycles. These will be explained a little more in a moment, and DC, cathodic and anodic current densities. The process can be used in pulse or DC mode, and both modes can be incorporated into a plating cycle. Let's have a look how pulse actually works. In this diagram, representing a drilled hole after direct metallization, we can have a closer look at what happens on an enlarged image of the whole wall. The additive system contains active components which are characterized by having different properties depending on the orientation of the additive molecules. One part of the molecule contains sulfur groups which attract the molecule to the copper substrate, and another opposite part of the molecule contains groups which attract the dissolved copper in the electrolyte towards the molecule. During normal DC plating, where the current is always positive, the additive molecules arrange themselves at the substrate surface. The sulfur groups help the molecule to stay on the copper surface, and the other part of the molecule helps to attract copper to the surface from the electrolyte. This maintains the efficiency of the plating reaction. However, this arrangement is so efficient it is very susceptible to current density variation, and in this exaggerated example gives rise to typical and associated variation in copper thickness. During the reverse phase of pulse plating, when the current is moving in the opposite direction, the reversal has the same effect on the additive molecules, which flip over. In high current density areas, for example on isolated features or on the knee of a hole, layers of molecules can build up on top of each other. When the current reverts back to the DC phase, it takes a little time for the molecules to reorientate themselves, and the plating in high current density areas is actually inhibited, as shown here in this exaggerated example. So the full effect of the reverse phase can be to plate more copper in the hole than on the surface. This sequence of events is also referred to as polarization. The periodic reverse pulse plating cycle typically comprises of a continuous cycle of normal DC plating with regular periods of reversal. This gives the overall effect of evening out the plating thickness, as is represented here. Let's quickly look at some of the terminology used when describing a pulse cycle. The two main elements involved are time, measured in milliseconds, and current, measured in amps. The current is either positive, as in normal DC, direct current, or negative. A cycle comprises a main section of DC plating followed by a much shorter pulse of reverse current. For the CU110 system, the forward phase lasts 10 milliseconds. The reverse phase lasts 0.5 of a millisecond, but is typically twice as strong as the forward phase. This is where the ratio terminology originates. For a ratio of 1 to 2, the reverse will have twice as much current as the DC phase. Ratio can be anything from 1 to 1 up to 1 to 12. Here is a typical oscilloscope readout showing an actual pulse cycle during plating. In this case, there is a forward current of 105 amps and a reverse current of 210 amps, and the reverse pulse is every 10 milliseconds. Some specific points should be made about a bath setup for CU110. Anodes for the system should be phosphorized deoxidized copper, bar or balls in titanium baskets. We can advise an optimum basket size, ball diameter and arrangement. air agitation or eductor solution movement should be used along with cathode rail movement 0.5 to 0.8 meters per minute. Electrical connections must be sound. The higher currents used and demands made by pulse cycles on equipment will highlight any poor connections with the resultant loss of pulse wave being applied to the work. Bath geometry is important and advice can be given to achieve optimum setup. A separate detailed guide giving recommendations for optimum setup is available to customers using or intending to use the CU110 process. At Schlotter, we constantly invest in the future. The PRT 2200 process is designed to operate with insoluble anodes and is showing very encouraging results. Thank you very much for listening, and I hope you have found this informative. Please do not hesitate to contact me for further information or if you would like to discuss anything in this presentation in more detail.
Okay, thank you for listening to that. That gives 3 areas of surface finishing that we often talk about in the industry. I'm acutely aware that I haven't discussed digitalization in any aspect whatsoever, and I'm not going to actually, because Chi, I think, gave a very eloquent overview of digitalization of electrolytic processes, and I'm not going to add to that. So I'm going to stop sharing, and hopefully we're back to the beginning.